Yeah, perfect. Perfect.
Perfect. Okay. Janakra sir. Shall I start, sir? Good morning, ladies and gentlemen. Welcome to Day 2 International Conference on Civil Engineering Trends for Sustainability, CTCS 2022, organized by the Civil Engineering Department, NMM Institute of Technology, ITTE. I, Dr. Bojaraja, the organizing secretary of CTCS 22, take this privilege to welcome you all on behalf of the organizing committee of the Civil Engineering Department. So, the glimpse of the day one report I am just presenting after the inauguration of ICETE 2022, the keynote one was delivered by Professor Nagesh Kumar D, IISc Bengaluru, on the topic Deep Learning and its Application in Civil Engineering. So, followed by there were four parallel technical sessions. So, today we have with us Dr. Chandan Kumar, Postdoctoral Associate, Mississippi State University. I request Miss Akila, Research Scholar, Civil Engineering Department, to introduce today's keynote speakers.
Good morning, everyone. Today, I am privileged to introduce to you our guest and keynote speaker, Dr. Chandan Kumar, Postdoctoral Associate, Department of Plant and Soil Sciences, Mississippi State University, United States. He did his previous postdoctoral research at the Colorado School of Mines from March 2021 to June 2022. He did his PhD in geological engineering from Michigan Technological University in 2020. He worked as an assistant professor for the geoinformatics program at Rajiv Gandhi University and Northeastern Hill University, India during 2015 to 2017. He completed his Master of Technology in Remote Sensing and Geographic Information System from National Institute of Technology, Karnataka in 2015. He has completed his Bachelor of Technology in Geoinformatics and Geotechnology from Bharatidasan University in 2013. His research interests include geological exploration, geohazards, precision agriculture, geospatial applications, spatial modeling, and machine learning. He published around 10 peer reviewed research articles with more than 200 citations. He achieved several awards, including an Outstanding Scholarship Award, a Doctoral Finishing Fellowship, travel grants, and the Best Presentation Award. He has presented at more than 25 national and international conferences or meetings. He is a reviewer for several reputed remote sensing and geoinformation journals. He is also a member of Association of Environmental and Engineering Geologists, American Geophysical Union, and International Society for Photogrammetry and Remote Sensing. On a final note, we are grateful for his virtual presence among us today. Without further ado, join me in welcoming Dr. Chandan Kumar sir. Over to you, sir.
Thank you very much, Keela, for introducing me. Before I start my presentation, I would like to express my sincere thanks to the organizing committee and Department of Civil Engineering for giving this opportunity to share some of my research work, which I did in last 2 to 3 years, uh, to the audience. And I would be more than happy to interact with uh, to all of you if possible, or if there is no time, we can also have a conversation through our email, and I would be also happy to share or express some of the ideas uh, if some of you are interested in pursuing master's, PhD, or postdoctoral research in in US. So if you'd like to hear any of this stuff, please email me at my email like ckumar@mtu.edu, and I would be more than happy to help you in getting some of the positions, or I would like to guide you in getting those positions. And I hope my screen is visible to all of you, and the voice is clear so that I can start my presentation. Today, I'm going to talk about hyperspectral data and, in general, their applications in varieties of fields, where my focus is going to be more on geological exploration, and also like some of the latest or recent spectral and machine learning approach which we have adopted in geological exploration. With this, let's see what we're going to discuss today. So we will have some background information on hyperspectral and some of the methods and machine learning, etc., and followed by the classical hyperspectral data analysis, their applications, and more important, some of the case studies on mineral exploration and geological mapping using hyperspectral data and different spectral and machine learning methods. And we will discuss those case studies in detail. And in the end of the presentation, I would be more than happy to answer any of your query or discuss in detail. So let's start with the background on hyperspectral. So hyperspectral remote sensing is a branch of remote sensing where the sensor has capability to measure the Earth's surface, uh, the reflection or electromagnetic radiation reflected from the Earth's surface or material, uh, in a way that you can acquire a complete spectral curve within the spectral domain. And those spectral curves are very important in identifying their type, or making some set of discrimination among different type of materials we have, or making some set of characterization of those materials. uh, just in simple words, if you see the hyper means many, and spectral is basically spectral bands or channel. So the hyperspectral remote sensing consists of many narrow continuous spectral bands so that we can acquire the spectral data, or more important, the spectral curve. uh, I will take example of the, like, if we go back to 10 to 20 years, we had hardly 2 to 3 channels in our television, like DD1, or I think we call as a DD Nationals, and another 1 or 2 more channel. In that case, we were kind of limited with what we can, or what set of information we can derive. But today we have more than 200 or 300 channels. So it is up to us what set of information we are interested in, and we can use those channels to get all the information which we are interested in. For example, if somebody is interested in watching football, cricket, badminton, volleyball, etc., we have options to watch all of them together, I mean, simultaneously. But earlier days, we did not have had those options. So very similar, like hyperspectral data, you get opportunity to get a spectral curve which is more continuous in nature as compared to your multispectral data or multispectral remote sensing. So as multispectral is basically limited with few number of spectral bands, whereas hyperspectral you get opportunity to have more number of continuous spectral bands. We will have a look at this figure so that we can understand in much better way. When you had just one band, so you get one value. When you get multiple bands, you get multiple values. So when, in simple words, you have one channel DD national, now you have 3 to 4 channels, and now you have more than 200 or 300 channels. So here you get flexibility to choose what information you are interested in, or you can use all these information together to come up with some of the informations which you are interested in. The classical methods of hyperspectral data analysis basically limited or basically deals with spectral data processing and spectral data classification. And the major limitation of spectral data classification is that it required some set of threshold value to obtain final map of your targets or your target. So for example, if you are interested in mineral mapping, or if you are interested in say you are interested in measuring the strength of materials, so you want to have some set of threshold value to get the final results. Whereas in recent years, we have seen machine learning have shown great success over most of the conventional classification methods. But we also know that machine learning required a good amount of training data, so that you can train the machine and machine can learn the data pattern or data structure and make a final decision or prediction. Whereas the advantage of spectral methods is like you can work with single training data and get your training or get your output, whereas in the machine learning you require a good amount of suitable training data sets. So the idea here is why we cannot use these spectral methods to derive the suitable training data, and then we can use in machine learning to obtain accurate results as compared to spectral methods, or to overcome their limitations. And today we're gonna focus more on geological exploration, and I will present some of the case studies. So we will see how we have used hyperspectral data in geological exploration. Some of the hyperspectral data analysis important task includes like pre-processing, which basically deals with preliminary noise removal and atmospheric corrections. So most of the time when you acquire data, you don't want to have the atmospheric attenuation, so that whatever information you are deriving is possibly coming from your target. So let us take example that on Earth surface. So you are interested in what type of minerals are present on the Earth surface. But when you capture the data, you are not only getting the reflected energy from the surface, but also from the atmosphere in terms of scattering or other phenomena. So it is very important to do the pre-processing, followed by spectral and spatial data reduction. So as I was saying, hyperspectral data consists of lots of channels, means you have many information, a lot of information available, but it is possible that all the information is not important to you. So you would like to you know separate or segregate the most informative information as well as you would like to discard some of the least important or noise. Take example of our channels. So today we have 400 channels. So not all of us are interested in all 400 channels. We might be interested in just 10, 20, or 50. So you want to have the most important channels with you, so that when you open your television, you don't have to search by each and every channel to find out, okay, which one you are interested in. So very similar to the normal televisions, we also perform spectral and spatial data reduction. Another important task here is in-member extraction, which is in general term is basically a step where you get the training data. But in hyperspectral terminology, we called as in-member, because that in-member is a member which is the most representative member of the entire class. So for example, in a class, we have some class representative. So like you if you want to have some information from the class, you call that representative and try to take feedback, okay, what is happening in class or something like that. Then you have the spectral analysis, which basically deals with the different processing with the spectral curve, like you would like to measure the shape or how the absorption features are there, how much depth in that those absorption feature is. We can estimate all those stuff using spectral analysis. You must have heard about derivative analysis. So we also do some of the derivative analysis to highlight the minute variations within the spectral curve, so that we can extract the important information. Then we have some of the classification or mapping methods to do classification of your targets, followed by the accuracy assessment, because you don't want to have results without saying that okay, how accurate your results are. So that you must know what is the accuracy of your experiment, so that you can trust and you can use reliably for research or operational purposes. The advantage, or I would say the capability of hyperspectral is not limited to any of these fields. You can, I mean, people are using hyperspectral techniques in most of the fields which we are aware of. So we will focus more on geological exploration, and we will use some of the case studies to see how we have done some of this stuff. Uh, the case study one deals with the hydrothermal alteration mineral mapping using hyperspectral data, which is average NG. Uh, and we have also developed an approach of threshold selection. So as I was saying in the beginning of my presentation, that the spectral methods has, a limitation that it required a threshold value. Okay, and most of the common approach is like trial and error based approach. But when you're working on a known site or at a very larger area, a trial and error approach might not be suitable in most of the cases. So you need to have some statistical, or you need to have some scientific basis to say, okay, you are using this threshold value, and you know how much accuracy you can expect from you by using the threshold of different methods. And we published this research in International Journal of Remote Sensing in 2020, and we'll see what we have done in this and how we can use in other research. Little bit on specification on the hyperspectral data. This is the name of the sensor, which stands for Advanced Visible Infrared Imaging Spectrometer, next generation, which was available right from 2017 or 18 to still we have. And the best part is, so all the data which I'm going to present here is basically has come from a joint adventure of NASA and ISRO, where the NASA has provided the hyperspectral sensor, and India, and particularly, and the ISRO have used that sensors to acquire the data in India for variety of applications. So you have applications like forestry, vegetation, water resources, soil sciences, geological exploration, and many more other applications, urban mapping, and etc. Also, we have hyperspectral data available, and now we have free access to those data sets. You can, if any of you are interested, just browse every NG NASA data. You will find the data. You will find the link to download. And you can see you have approximately more than 400 channels. And the spatial resolution here was, in my case, the data sets which I have used is approximately 5 meters of spatial resolution. Means you can see any object of 5 meters or slightly larger than 5 meters from the image very easily. Anything which is less than 5 meters would be very much hard to identify from the image, because the pixel size is 5 meters. This is the study area. I'm 100% sure that all of you are aware of Karnataka and Raichur district, and there is a gold mine known as Hatti Maski gold mine, which is one of the most important gold mine in our country. And here is the geological map where we are seeing different type of rock types, and also some of the gold occurrences which were identified from the Geological Survey of India. We have taken from those maps to locate some of those most important locations for the gold occurrences. Uh, this is the hydrothermal alteration minerals, spectra of hydrothermal alteration minerals. So I guess I missed to say that hydrothermal alteration minerals are very, very important when we work in geological exploration, because these minerals works as a proxy to identify the economic ore bodies, or I would say ore bodies. The distribution of these minerals can help us to narrow down our area of interest on the field for extensive field laboratory or geochemical or geophysical surveys. You might be thinking of what are these three spectra. So you can see that the blue spectral curve basically derived from the hyperspectral data. In short, we are calling like image spectra. The black spectral curve is basically the laboratory spectra. So we have used the spectroradiometer of the same wavelength range. We collected the rock samples from the our study area, and we kind of looked what are the minerals available across the study sites. And the red spectra is the USGS, that is basically US Geological Survey spectral library, which is very standard in the hyperspectral domain. That most of the time when we use hyperspectral data, the USGS spectra used as a reference spectra format for material identification or discrimination or classification. So these hydrothermal alteration minerals were very important, and we also found in literature that these minerals have close association with the ore bodies in our study area. We also have some non-target spectra. So what is this non-target? So any spectral curve from the Earth surface which doesn't belong to our mineral categories has been categorized as a non-target spectra. So it could be soil spectral curve, it could be the barren rock surface spectral curve, it could be the mixed spectral curve of the soil samples or the rock samples. And we have used these non-target spectra to find out. So we have used this non-target spectra along with your target spectra. So target spectra here are mineral spectra to identify the possible optimum threshold, so that we can get the complete classification map of the entire area, particularly the mineral classification maps. Let's see this. So this is basically a matrix of your target and non-target spectra. So your target here is again your mineral classes, and non-targets anything which was not minerals. So the spectral similarity matrix of target and non-targets is helping us to find out the most possible optimal threshold value which is required for most of the spectral classification methods. So take example here. So GOE stands for goethite, which is one of the most common mineral, like iron or iron mineral, I would say. So if you wanna classify or identify goethite, my threshold value should be less than 0.07. Anything which is close to 0.07 or higher than 0.07 would increase the chances of inclusion of NT3, which is my non-target. We are not interested in this, into the inclusion to goethite class, which you don't want to do. Means if you want to classify goethite, your target is okay, or your goal is to get the goethite class as much as accurate as possible. You don't want any other class. You don't want mineral classes getting mixed into this, or you don't want any unwanted classes. So this is basically the matrix of target and non-targets, which is trying to help us to find out the most or possible optimal threshold value. So in the classification, the most common approach is like we mostly focus on what we are interested in, but sometimes it also helps, if you're not interested in some of the classes, and if you know them, then your classification becomes relatively easier. Means you can achieve better success or better accuracy as compared to if you just stick with mineral classes. So for example, if I would have just stick with mineral classes, we would not be in a position to know what could be the possible threshold value to get goethite mineral output, right? And we compared this approach with some of the existing methods like the statistical method, we saw that some of the previous methods which were proposed in literature were not suitable, at least in our case. So see here, if you use 0.07 or 0.06, I mean, between these, any threshold value, the possibility of accurate classification of goethite class by using this classifier, which is basically spectral angle mapper, is approximately 7%. But if you use cutoff 0.05 to 0.045, your accuracy goes around 85% or higher than that. That is very similar to which is kind of in chloride or for different minerals. And we compared this approach with the existing statistical method, and let's take example of goethite. So SM2, which was suggested by Hecker et al. In 2008, suggests that 0.08 could be the possible optimal threshold value for goethite class. But we have seen here very well that if you use anything which is greater than 0.07 or higher than that, basically you are including NT3 into the goethite class, which you don't want to do, because if you do so, you are not getting goethite mineral classification map. You are getting NT3 into the goethite, which you don't want to do. And this is the final hydrothermal alteration mineral map using the spectral angle mapper and of course by using the optimal threshold, and you can see the distribution of hydrothermal alteration minerals. So this site belongs to the main mine in the study area, and we had lots of chlorite deposit in the area. And here we can see some intrusive which were more of iron rich some materials. So and then we have used the field samples and another geochemical analysis to validate our results, and we found that the alteration mineral map acquired or derived using hyperspectral data were very much effective in getting the final distribution map of alteration minerals. I hope this was okay to understand, and then we will move to next case study where we are proposing new spectral matching measures for hyperspectral data analysis. So the whole background of this research is when you are making a discrimination between apple versus orange, it's very easy for anyone to pick, okay, this is orange, this is apple. But if I ask you to make a discrimination between 10 type of apples and ask you, okay, find out the varieties of them, then it becomes very difficult. Means you need to have a good understanding of varieties of apple, then only you can identify, okay, which one is which apple, right? So very similarly, in real life scenario with hyperspectral data, the spectral curve of different materials show higher similarities. Then you need these spectral matching measures that can measure that can discriminate them accurately. So that is what this all research about, and we published this research in International Journal of Remote Sensing in 2021. So we used a wide range of hyperspectral data like USGS spectra of minerals and vegetation, and we also added some noise into the spectra, and then we also mix the different spectra with different proportion, just to increase the similarity between or similarity among them. Because as we know, as you know, that when you're I was saying, when you are comparing apple, or when you are making a discrimination apple versus orange, very easy. But when you have to make a discrimination between 10 type of apples, then it becomes very challenging job. So here is basically, here what we were trying to do, we are adding random noise and into the spectra of vegetation and minerals to increase the similarity. And also we perform some of the linear mixing of the spectra to increase the similarity among them, so that you are testing the algorithm with tough or tougher situations. We have also used the real hyperspectral data acquired from the airborne platform, what we have used in our previous presentation. These are some of the most commonly spectral mapping measures in hyperspectral domain, and these are some of the newly proposed, which we proposed in this study. Uh, and we used evaluation measure called as relative spectral discrimination power, because the value of these cannot be used to compare them to evaluate their efficacy in discriminating different spectra. So you need a measure which can help us to identify, okay, if you have 5 methods or 4 methods, which method has higher discrimination capability. So this statistics is giving you the same stuff. If you have higher value, that means that particular method has higher capability to discriminate the discriminate your different materials, or basically different spectra of materials. Let's see the results of so in simple words. So Al is basically a mineral called as alunite, and Cl is basically chlorite. So when you are making a discrimination between alunite and chlorite, you can see that some of the methods, performance of some of the methods are relatively less as compared to some of them. So you are interested in a method which can help you to discriminate them accurately as much as possible. And you can see that in most of the cases, the bar which representative in brown color indicates very high discrimination capability. And this method we proposed in this research. We found very similar results when we tested with different vegetation spectra, and very much similar results when we tested them after adding the random noise. As I was saying, we have also used the spectra with random noise, and after mixing the spectral curve of different minerals. So in most of the cases, we saw that the newly proposed method, which have shown great success over the existing method. And it is only due to the fact that the existing methods were not efficient in handling noise, and particularly when you have higher similarity between two spectra or multiple spectra. What I'm trying to say here is, if you're making a discrimination, if you're asking your existing method to do the discrimination between apple versus orange versus grapes, those methods were perfect, no issue at all. But when you are asking them to discriminate apples, varieties of different apples, then they were facing the issues. So we found that the existing methods has shown relatively lower discrimination capability as compared to the proposed method in most of the cases. In some cases, we found that the existing method were performing as good as the newly proposed method, as well as at some occasions we also found that they were still better, slightly better. But those cases were very rare. As so if we are making discrimination 10 times, 8 to 9 times the newly proposed method were performing much better, much better than the existing method. let's see our second case study where uh, we will show how we have integrated the spectral enhancement techniques and machine learning together to overcome their limitations to produce accurate lithological classification using average Senji hyperspectral data. And we published this research in International Journal of Applied Earth Observation and Geoinformation in 2020. Uh, uh, if any of you can help me to know how much time do I have, Dr. Bhojraj or Dr.
Another 15 minutes.
Okay.
Okay.
Thank you very much.
Thank you.
So in this case study, we will see how we can use these spectral and machine learning methods, basically, and more on integrated approach to do the job in accurate way. Okay, just a moment. I think my okay. Sorry for interruption. Like it's automated
That's
light,
okay.
so it turned off. Sorry for the interruption again.
That's okay.
So here what we did is we used a different spectral enhancement techniques. So false color composite is one of the most simplest enhancement approach where where you try to find out the most important combinations to discriminate different type of materials. In my case, these all are rock types, so I would say to discriminate rock types. And principal component analysis and independent component analysis, these are the two most popular feature extraction or spectral enhancement techniques we normally use to discriminate or enhance the spectral contrast between rock types. So you can see that in the false color composite, the discrimination between discriminating different rock types were slightly harder as compared to PCA and followed by ICA. So PCA and ICA it's like complementing each other. What I'm trying to say, in PCA, say for example, in PCA, rock type 1 and rock type 2 is being discriminated very well, whereas in ICA is helping us to discriminate rock type 2 and 5. So we use these two methods, or I would say all these three methods, to get a reference lithology map, because you need, as I was saying, machine learning required suitable training data in good quantity. So you want to have a reference map which is more robust or more reliable. Whereas if you compare the reference lithology map with your geology map, you can see in geology map you hardly have this class, which is basically your black soil, the well-weathered surface. And um, another limitations with the conventional geological map is they were prepared for larger scale. Means larger scale always will have less information, but wide coverage, whereas lower scale will have good amount of information, but less spatial coverage. So we use the different principal component analysis and independent components analysis to derive a reference lithology map which suits the resolution of every NGA data, followed by, and then we use this map to get the different training data for different classes. And you can see that the distribution, the sample is widely or well distributed, because you don't want your training data skewed in, or you don't want to be biased to select your training data only in few areas. You want to have a training data which is well distributed so that it represents the entire data structure, possibly the most important data structures. And you have some validation and validation points also, like after getting the reference lithology map, we had a collaborator from National Remote Sensing Center, which, and he was basically helping us to get the some of the field samples or to evaluate the our image results. This is the different spectral curve of different rock types and their box plot, which basically explaining us the data range. And this is the training data statistics. And you can see that you have a fair number of training and testing samples. The idea here was to to see the effectiveness of different approach. Like you have all the bands, all the suitable bands, then you also have some in geology the SWIR bands, that is basically short wave infrared bands, are considered very important. So we were kind of exploring, uh, is it true in lithological classification, because geologists mostly rely on SWIR, which is short wave infrared bands, because most of the rock forming minerals show strong or important absorption feature within that wavelength range. But when you make a classification, or when you work on a classification problem, you also need to consider some other wavelengths like VNIR, visual near infrared bands. So this is the accuracy of different methods, different machine learning models like linear discriminant analysis, random forest, support vector machines. We just tested three methods because these three methods basically touches the three different type of way of doing the classification. And we found that JMIM bands, these are basically the bands derived by using feature selection method. So feature selection method helps us to select the important variables. So as I was saying in the beginning, that even though we have more than 200 or 300 channels today with us in our television, but we do not watch all 300, or each or every time when we open our television, we do not switch each time all 300 channels to see which one is good for us. So you want to have a more robust way to do, and feature selection is a very important task in getting the most important variables or spectral bands. This is the principal component analysis bands we also tested, and what we found that the number of bands here were, here we had 300 bands, here we have around 150 bands, and here we had around 50 bands, and here we have 100 suitable bands. And we found that PC bands or JMIM selected bands were good enough in producing the accurate lithological map of the study area as compared to your SWIR bands or all spectral bands. And this is the overall accuracy and copper coefficient of different methods for different input features. So to conclude, we can say that okay, PC based bands and JMIM based bands were suitable or were performing much better than SWIR or all bands. Another thing to note here, that when we make any classification or when we make any decision, we don't want to be too complicated, or we don't want to make a decision which is too complex, because if you do so, your decision is going to be very tough. In machine learning language, we say that you don't want to have a complex model, because a complex model always have a tendency to overfit the data. What I'm trying to say here is they try to learn the noise or uncertainty which we always have in our training data, and then they try to overcompensate with the noise, and they learn the noise considering that is the correct information. So you don't want to have a very complex model, and one way to reduce the complexity is to reduce the number of variables, and that we can do by using PCA, which is basically a feature extraction method, and JMIM is basically feature selection methods. So these two techniques basically helping us to reduce the number of bands so that we can achieve success, but it is not going to be too complex. And this is the final classification map by support vector machine using the JMIM based bands, and you can see that it matches very well with the reference lithology map. So reference lithology map is like considered as the accurate, the ground truth information, even though there are higher chance that your reference map will have some uncertainty, but you have to accept that you may not expect 100% truth or 100% accuracy in your task. This is our fourth case study where we are trying to show how you can integrate multiple data sets together to achieve success in your classification. In our case, we had rock type or lithological classification. So we published this result in 2021 in GeoCarto Internationals. And we used here different data, like we used the multispectral data, we also used the microwave remote sensing data, and we also used digital elevation model. So microwave remote sensing has a capability to penetrate through few centimeter of the surface, particularly on the loose sediments or loose surface. It has another advantage of this is like it is very sensitive to your textures. So we would like to, so here what we were trying to do is we were interested in using this data to derive some of the texture information or as well as morphological informations. And the study site again is in India, in Madhya Pradesh, and Chhatarpur. So again, it is the area is, all these sites have been chosen because of their geological importance. So it was not like random selection. All these sites have some geological importance. That is why we selected those sites to study their different rock types as well as to study hydrothermal alteration minerals. You can see you have the training data, and I would like to bring your attention here. Let's see CB and FEST. So if you see this box plot, these are very similar box plot. Means your spectra is going to be very similar. Or if you are making a discrimination just by using multispectral data or any spectral data, you may face challenges because these two appear to be very similar. So that is why we were interested in using other information, for example textures, for as well as morphological features, because over a period of time different rock types have different tendency to to show the surface signatures, like few rock types which is very hard, that they will have very less weathering, whereas soft rocks will get weathered soon, so that will have different texture as compared to your hard rocks, as well as morphology. So we use the digital elevation model and different microwave remote sensing data to derive their textures and morphological features, so that all these features can be used to complement your spectral data to improve the classification of different rock types. And we use the again feature selection methods to find out the optimal number of variables. As I was saying, you may have 200 variables or 200 channels, and all those channels might not be useful to you. So you want to have the most useful channels. In our words, we will say the most important variables, and these variables were extracted using different data sets, using feature selection and feature extraction methods. And we can see that the data type or data or input features D and E is performing much better than A. And if we compare the accuracy, which is when we use just spectral data, and that is approximately 60 to 62% for SVM and random forest. And if we integrate all the data sets together, we could get the accuracy more approximately 75%, which is approximately 15% of improvement in your overall accuracy. Again, one thing to note here that it was not just blind integration of the all the data set, because if you do so, sometimes what happens, if those variables are not important, they will reduce the accuracy of your model or your classification model or classification method. So you should always have some statistical way, like feature selection. We always use feature selection, which helps us to identify or estimate the relative importance of each variable. So you know which variable is more important, and you can always play with the number of most important variables and see how many important variables is important in your study to get optimal results. So the in our case, the optimal number of variables were 30, whereas the all if we sum up the all the variables which were around 50, around 60, means we are basically reducing 50% of variables and achieving much better results. So this is the lithological map. This is your reference lithology map and the lithology map which we derived using random forest and its support vector machines. And again, all these so machine learning and methods like random forest and its support vector machine, it has several tuning parameters. So and all these parameters were optimized to get the final map of the rock types or lithology in the area. To summarize, we saw that hyperspectral data has been effectively used in hydrothermal alteration minerals, and the proposed method, particularly the spectral similarity matrix of target and non-target, shown to be very promising in finding optimal threshold value, which is needed by most of the spectral mapping measures. So the developed approach is not limited to only one method. It can be used in any spectral mapping measures. Second case study, we saw that the developed spectral mapping measures were quite effective in discriminating two similar spectra, apple versus apple, as compared to existing spectral mapping or spectral matching measures. We also saw that when you use feature selection and feature extraction methods to select most important variables, in our case spectral bands from the hyperspectral data, we could achieve better accuracy in lithological classification. So all these results which we have seen today is not it doesn't mean that it is going to be applicable only in geological mapping. We can use the same approach in forestry, in discriminating different forest species, or in civil engineering. We also work on material identification, material strength characterization. So we can also use hyperspectral data to acquire the spectral curve from those material and see is there any spectral difference between a strong material versus slightly less or weak material, and we can always use them for modeling purposes. And in the last case study, we saw that when you do the optimal integration of different properties of rocks, you could there is a higher possibility that you could improve the accuracy of your lithological classification. With this, I would like to express my sincere thanks. I really appreciate and I'm honored to given this opportunity, and I would be happy to answer your queries. And if any of you are interested in knowing or if you required any guidance for higher educations like PhD or postdoc in US, I would be more than happy to help you. How much? And these are some of the emails you can use to get in touch with me. And all the presentation which I uh, did today was part of NASA. I mean, the research was supported by the NASA grant and Michigan Technological University Fall 2020 Finishing Fellowship. With this, I would like to say thank you very much and happy to take your questions.
Thank you. Thank you, Dr. Chandan, for the informative session. Is I
Thank you very
audible?
much, Dr. Gujras.
Yeah.
Yes, thank you very much, Dr. Gujras.
There are a few queries from the participants. I will just read out. The first question goes like this: what bands can be used for vegetation classification? Where do we get the spectral library for Western Ghats vegetable?
Okay, so yeah, so like in the vegetation, when you work on vegetation, so the most important wavelength range is VNIR. Particularly the near infrared spectral bands are very important in in doing the discrimination of different vegetations or making a discrimination between different forest species, because that is the wavelength range where the chlorophyll absorption bands of you have, and then you can always use them to make a discrimination. If you have the whole wavelength range, particularly from zero point 0.4 to 2.5 micrometer, then you can always use feature selection method to find out what are the most important bands you can use to do the vegetation classification. But in general, the VNIR bands are most important uh, uh, for vegetation studies. Second question is on vegetation spectral library. So you will get the vegetation spectral library, but it will not be, only for Western Ghats. So you have some vegetation type, and then you can find at a USGS spectral library. If not, then you can also explore NRSC website to find if they have any spectral library available. If they don't have, then you have to collect the spectral curve of those vegetation or plant by using the spectral radiometer. But in general, you will not find many spectral library for vegetation, particularly for Indian sites.
Thank you. So there is one more question. I will just read out. So is it possible to acquire the hyperspectral data in a cloudy weather?
Okay, so whenever you have cloudy weather, you don't want to collect any type of multispectral data, because your multispectral sensors is very much sensitive to how much electromagnetic radiation is coming up from the surface. So no, you don't want to collect any data from when you have a cloudy weather. Of course, when you have microwave, so microwave sensors can penetrate through the cloud, but hyperspectral sensor cannot penetrate through the clouds.
So thank you. So I have one question. Um, so is there any the data available for the users, for our students and all, uh, freely, that to hyperspectral nowadays,
Yes.
other than Hyperion?
Yes, so Hyperion was our the first spaceborne hyperspectral sensor, whereas the you can get hyperspectral data not for all the sites, but for most of the important sites, right now you have every NG hyperspectral data available, which you can get freely. I'm not very much sure if you can access from the Indian website, but there are data sets available from the NASA JPL. If you just Google Everest NG JPL, NASA JPL, you will find the website, and I'm pretty sure you can access the data sets now. Before 2 years, it was not accessible to everyone, but now it is accessible to whoever has internet connection. They can download the data free of cost.
Thank you. So with
Mhm.
that,
Mostly.
we concluding the session. So those are all the questions from the audience. So we come to an end of the keynote lecture of day 2 in CTCS 2022. I take this opportunity to thank Dr. Chandan Kumar for his informative keynote address in our CTCS 2022 conference. Thank you very much, sir.
Thank you very much, Dr. Boja, for giving this opportunity. Thank you very much.
Okay, sir. We'll get in touch with you